one group leader.
I share.
You said you should, right. Okay, so you can send again. Yeah, no problem. It's okay. I start to get, so when you share, then I will get an email saying that you shared the model. But please put the model name properly. You just put V4. I don't know which group, which model. So after you download to my Dropbox, I don't know which this model is. The model name is V4. Nothing. So when you send the model, make sure your group number is before that, and then model name or something. Don't use V1, V2, model 1, model 2. I am getting millions of things every day, right? And your file will be lost. I cannot find it anymore. So please, whenever you send me something, make sure that you send it in a proper format, starting with the group name. So class, group, right? TB, tall building, group 1, version 1, something like that. Otherwise, I will have no idea what you send me. Okay? So please send me again, because that V4 is already gone. Okay, so today we talk about structural configuration for lateral loads. I think we started this a little bit last time, and today I will try to finish. So this will be last lecture on structural systems and behavior for lateral loads, and then we will go to next topic later. Okay. I want to spend some time now after that on design of components. So we will talk about that. Last Wednesday, what was the class by Mr. Ram?
Shear wall
Project,
design.
right?
Shear wall.
Shear modeling and shear wall design, right? Okay. So I mentioned to you that the efficiency of the structural configuration depends on how you put things together, and one of the most important observation is that when you connect two structural elements together in a different way, then the total stiffness of the system is more than the individual stiffness of the components that you connect, depending on how you connect them. For example, if you have two walls and they are connected by a flat slab which has a very small stiffness, so basically no connection in between them, then the total stiffness will be this wall plus this wall equal to 2. However, if you take the same two walls and connect them through proper shear transfer mechanism, then you can get far increase in stiffness. Here in this case, 8. So 4 times more than the stiffness of the same wall by putting the connecting elements in between them. The idea is that if you remember the first rules, I give you 4 rules. Try to convert the forces, lateral forces, into axial loads. So if you do this one, it will convert this into tension compression. Here, both the walls are bending, right? Independently, side by side, but bending. Here, in addition to bending, there is going to be axial force. So one is going to be in tension, one is going to be in compression. So as soon as you convert the lateral loads into axial forces, your system efficiency will improve a lot. So whenever you try to develop a structural system, see how you can convert bending into axial forces through shear, right? So here we are converting the bending into axial forces through the shear of these two elements. So these two elements are the shear links between two walls, converting bending into axial force. And this is, so here we can compare different systems with different behavior. So if I take the frame, simple beam column frame, which is primarily a bending mechanism because it is based on the bending of beams and columns. And then I add a wall here, but just connect it normally. And then I add 2 walls and just connect them simply. And I add a wall with the connecting beams, little bit big, and I add a wall with 2 very big connections. You can see the increase in stiffness. And you will also see increase in change in the axial forces in the wall by each addition. So this is one example where you can improve or adapt the system by changing how the systems connect to each other. And then you can see the efficiency of the system. And one of the efficiency is how much area the structural members are taking from the total floor area. Because when they sell the building, they sell by area, right? Usable area. And if the structure is taking a lot of the area, then they cannot sell that area. Usable area becomes small. So the clients are normally looking at how small your structural footprint is compared to the building footprint. And we normally measure it by wall plus column area. If you add the area of the walls and add the area of the columns in the plan and divide it by the total area, you get a percentage. So if the percentage of this area is small, that means you have a efficient system. If the percentage is large, that means you don't have a very efficient system. Cost will be high, and also the mass will be high, and so on. So this system, for example, uses about 11% of the floor. As you can see, so many walls and so many columns there, and it uses 11% of the floor. This model uses 7%. This model only uses 5%. They are almost the same height, 215 meter, 205 meter, 230 meter. So they're the same height building, roughly, but the use of the structural part is different, right? And one of the reason is they put a outrigger over there. Those are not linked together. So these are also linked by beams. So they try to improve the structural performance by coupling things together. And you can see the effect on the area, right? So now, as part of our design development, and once you send me the ETABS models, we will be able to calculate all these ratios. We have developed a program that extracts the data from ETABS model and calculates all the ratios, and then it can compare one system is better than the other or not after you satisfy the design requirements, right? How efficient the system is. So one of the things that I'm going to rate or grade your project will be efficiency also. How efficient is your system compared to other groups, right? So if your system is efficient, you will have smaller ratios, percentages. If your system is not so efficient, you will have larger ratios, right? So keep that in mind. So wall-only system, you can see this system has only walls. Of course, in this system, very large area of the structure is taken up by walls, but they don't need partition walls. So they use the structural walls as the partition walls. So it is okay because there are no partition walls anymore, no non-structural walls. All walls are structural in both these systems. So this can be also an option, right? And these are some uncoupled walls here and there, distributed walls. This is an example of single core walls, one core and columns. One core and columns, not many walls. So this is a coupled system where frame and walls are connected together by beams. You can see here beams running here, beams running here. So beams and frames work together. Here also core wall and frames work together. This is a coupled wall. So people have so many ideas on how to make a structural system. Walls only, coupled walls, distributed walls, core wall plus column, endless configurations can be created. Pure core wall, no other element. Flat slab and core wall, very common these days. A lot of people want to do that. Just construct a core wall and columns and flat slab, no beams, no interaction between them. So this is also possible up to a certain height if the core wall is big enough. Here also you can see coupled core walls. So this is a core wall, and here two core walls, and they are coupled by bracing. Very effective because this is a U-shaped building. So if we don't connect them, the ends of the U's will be very flexible. They will move like this. So they are connected by a framing and a diagonal bracing, so very effective over there. This is coupled walls, and they are connected together by flag walls and coupled walls. So you can use these combinations to create this system which is more efficient than the core walls alone. So coupled shear wall is very important, a very powerful way to design an efficient system. Sometimes we have distributed core, one core here, one core here, one core here. That is also one core, second core, third core. So if the building is long, you can distribute the cores, and elevators can also be distributed. Depends on the architectural plan also. Sometimes you just have, interesting project like this, just a core wall and the whole building is hanging on top of that. Now let's come to the very important discussion of BRB, outriggers and dampers and transfer systems in tall buildings. So the purpose of the BRBs and outriggers and dampers is basically to reduce the natural period. This is good for wind response, reduce top displacement, reduce drift, reduce moment, and this follows the all four rules of tall buildings. So if you put outriggers, it gives you the ability to follow. Do you remember the 4 rules? 4 commandments? I showed last time, don't say that you didn't see it. That I'm sure, because that's start of the presentation. Twice I have shown that slide. 4 commandments of tall buildings, once in the introduction, first lecture, and once before. So if you don't remember, that's not good. Just 4 rules, you cannot remember? I showed you by bringing one guy and showing you all the rules. Yes, now somebody start to shake hand, right? So please remember the 4 rules by heart, tall building. If you don't know the rules, how can you design? Go back, notes, find the 4 commandments, 4 rules for tall buildings. So outriggers help you to follow all 4 rules. They do not reduce the shear in shear walls. That is one thing you should remember. You cannot reduce the shear in core walls by putting outriggers or any combinations. That cannot be reduced. But moment can be converted into axial force, but shear cannot go anywhere. Shear has to be taken because shear is horizontal force. So you need horizontal shear to take that part. Only bending can be reduced, not shear. Shear can be reduced by other mechanisms. And this needs space to implement. The problem is that you need space to implement the outriggers, and sometimes the architects or the clients don't give you that space because you block some area that cannot be done. So outrigger is basically, normally outrigger should be like this. I think I showed this slide. This is the core wall, this is the outrigger, that wall over there, but it will block the way, so people will not let you do that. So physical outriggers are not allowed many times. So we use virtual outriggers. That means you put the outrigger not at the core wall, but outside, far from that, and it still works. And last time I asked the question how it works, and some people replied, some people did not. So now you remember that we talked about this. And then you can put a belt around that. So belt and outrigger, virtual outrigger, this is a good system. If you cannot put the outrigger inside, you can put it on another place, not directly to the core wall, and still it works. BRB, we have talked about it already, buckling restraint braces. These are very special braces which do not buckle, because normally braces buckle. The problem with the braces is that when the large compressive force comes, they buckle. And they, like this one here. So if you look at the response of a traditional brace, it is red line. So once you load it one time, when the load goes to compression, it will just buckle and lose its capacity. So the brace only works in one direction, in tension. And when you have compression, it will buckle. And once it buckles 2-3 times, it will break. So it will not be effective in tension also. So traditional braces are not good in tall buildings because they are going to buckle or attract a lot of force, and they have no ductility. Buckling restraint braces are specially designed braces. So this is a brace. It has 2 parts. One is a core inside and one is a shell outside. So the shell prevents it from buckling and the core inside yields. So we designed it in such a way that it yields before buckling. So there is no chance of it to buckle because it will yield before that. So it is a very good device that can provide energy dissipation and ductility without buckling. So inside, this is the core, the tube is very small compared to the outside. So when you have large force, it just simply yields. And it can keep yielding infinitely. So like that, like this loop. So it acts like a very nice damping device, also energy dissipation device without buckling. So outside you cannot see anything, but inside it's buckling and unbuckling, yielding and unyielding, yielding and unyielding. So this is a very, very, very good device. And we have used it in many buildings. It's a tall building, and these are the buckling braces installed there, 4 in this level, 4 in this level. So they act as outriggers and also act as dampers and also act like energy dissipators. So very good system. It reduced the seismic forces, it reduced the drift for wind, and it transferred the forces from core to the outside column and converting bending into axial force. So really, really good system. Then I think I talked about flag walls, and this is coming from the research last year. Flag walls are concrete walls that we place in a building, not randomly, different locations. So they don't go all the way to the core wall, but you just put them someplace and then connect them by a beam to the core wall. But they don't go all the way to foundation, and they don't. So these are not really outriggers. So you can call them partial outriggers. You can call them flag walls, right? They provide stiffness. They also control drift. They also provide some outrigger effect. And last year, 2 students worked on this topic. One was looking at flag walls for wind consideration, and one was looking for flag walls for earthquake consideration. And then later we combined their research into one paper which talks about flag walls for tall buildings, both for wind and earthquake, right? So this year also we have 5 theses looking at one problem in small pieces of one problem, and later we will put them together into one research. So that's how you can, many people can work together to solve a big problem. So this is one student outcome. This is second student outcome. So they've looked at different configurations, different way of doing things, and then found different locations, optimum sizes, and stuff like that. And we presented this in many international conference, this paper. Another one is staggered walls. That means you put these flag walls not in this manner, you use this concept, and you go all the way to the building. And we used this concept in Philippines long time ago. Very effective for controlling the building. It's like a truss, but through the walls. Then you have isolated flag walls, just placed here and there, randomly, following this rule. And this also works. You can see from here. This also works to control drift and control the forces. So use of these ideas are new a little bit, but the important thing is to understand how to do this, where to place them, which is the most effective location, what are the issues with having these walls. Because one of the issue found by the researchers is this connection. They said the connection between this one and slab another is something that attracts a lot of forces, so need to be designed. So you have local problems that need to be solved. So once we understand all of that, then we can use them in building configurations. So this is overall view of how you can create systems by combining things together. So let's look at a little bit more detail on how this works and why it works and what we need to understand for the systems to have a good efficiency. So rigid frames, as I mentioned, you already know the most common basic structural framing system. It works by having rigid connection between columns and beam, and you have, it is good up to 25 stories, 20 stories. Beyond that, it will not work well. in fact, the building codes require that even if you have a shear wall and a core wall, you must have at least a frame which takes 25% of the forces. This is something that we don't agree with, but the codes require that to be done. And that requirement, in fact, this year one thesis is about this topic, that what if we don't follow this rule, and what if we follow this rule, what are the differences in performance and so on, right? So we're looking into this particular provision in the code, because code requires that if the building is taller than certain height, then you must have 25% of the forces resisted by frame. But in tall building, that is not practical, not possible, because in tall buildings we have very few columns, mostly it's core walls, you have seen. So those columns and frames cannot be capable of resisting 25% of the force. It's not possible. So if you try to do that, then that means you have to over-design the columns and beams too much to resist 25% of the force, because they actually get only 5%. But if you insist that they must carry 25%, then you have to increase their reinforcement and sizes too much, because not enough frames there. So that's why this provision is not practical, very uneconomical, and not logical also. So this is how rigid frame works. As you know, as I mentioned to you, it starts from the shear in the column. From the shear in the column, it creates a bending moment, and in the column, from the bending moment, this one here, and then it creates the bending moment in the column. From column, it goes to the beams. So I've said many times that in lateral loads, the forces start from the column shear, move up to column bending moment, and from column bending moment, move to the beam moment. Gravity load start from the bending of the beam, creating bending moment in the beam, going to the column, totally reverse. And this direction can be negative, positive. So depending upon which direction force is coming, gravity load is only one direction. But earthquake, wind can be both directions. So that reverses the direction of the bending moments all the time. So one time it could be positive, one time it could be negative. So we have to consider both direction. This one negative, this one positive, that one both direction. And that makes it hard to design things, because it's changing the direction. So rigid frame behavior, I gave you an assignment on frame. You remember I said equivalent frame when we talk about the gravity load system. People forget. I showed you exact picture from gear, and I said if you have columns and beam equal size, then it will happen like this. If you have bigger, please go back and look at that slide where I plot the bending moment from different combinations of these three cases. I showed you in a slide in which I plotted the bending moment diagram, and I showed that what is the effect of the gravity load on the column moments and beam moments. Now we are talking about another aspect. What is the effect of the lateral response on this issue? So this is a normal beam column. This is when beams are much stronger than column. This is when columns are much stronger than beam. This is the typical case if you use flat slab in a tall building. Even with a beam, this is the case. Why? Because columns are very big. Because of the gravity load is too high. Beams are not that big comparatively, or it's a flat slab. So if you normally have this case in tall building, you have this case in very short building, and this case in a medium-rise building. So if the building is only 2 floors, you will have this case. If the building is like 10 floors, you will have this case. If the building is very high, you will have this case. So these 3 cases are very real, and they produce different behavior. So you can see from here deformation. Here, very large deformation. Here, deformation is less. Here, deformation is large. So it can be concluded. What can we conclude from here? Come on, I have been talking about it since morning. what can we conclude from this diagram, this behavior? What is the key difference between three models? Yeah, no, model, not displacement, model, original model. Why this behavior is different?
Lateral stiffness.
Huh?
Lateral stiffness.
No, not lateral stiffness.
Relative stiffness of column.
Yes, but no, again, go back one more step. Please try one more thing. Not relative stiffness alone. That's too general. That's too, try to be more, be an engineer. Last attempt, anyone? Sorry? Cross section? Cross section, okay, we understand, but what is the impact of that cross section? I'm trying to ask you. I just talked about it since morning about this issue. Outrigger effect. Outrigger effect, that means transfer of the lateral forces from one element to the other element through shear. This is exactly the same thing is happening. Here the beam is very large, so it has large stiffness, so it can transfer the forces from one column to the other through its shear stiffness, which is large, right? That's why you have small displacement here. Here, even columns are very big, displacement is very large because they are just bending. We are not able to convert the bending into shear and axial forces. You understand? So remember always, the lateral displacement of the tall building cannot be controlled by columns stiffness. It can only, or shear wall stiffness alone. It can only be controlled by connecting the vertical elements by strong horizontal elements. I just talked about this so much and you did not get the concept. Vertical elements, either walls or columns, even though very big, they cannot alone take the lateral forces well. You need to connect them by some strong shear connections, strong horizontal connections. This is the same thing here. Right? Please think. I spent so much time making these, things for you, and for you to be able to. Anyway, you can see here the beam is not bending here; they are almost straight, right? That means they are very stiff. Here you can see the slab is deforming. That means it's not. Here also the beam is deforming. So you can even see from that alone that deformation of the beam is causing large displacement. Here the beam is nearly straight. So that means beam's deformation is not adding to the frame deformation. So you can see from the bending moments, here negative positive, here only one direction. So that means column is not undergoing double curvature, it's just bending like a simple cantilever. It will not be so effective. And if you look at the shear on that point, you can see. So you already have frame 2D? Last time they gave you? Did you get the frame 2D app? Yes, no?
Yes.
Did you finish the two assignments on that frame 2D app? Yes, no?
Did the app.
So why don't you finish the assignments I gave you a long time ago before the midterm? And I said,
We don't have the assignment.
yes, I gave you assignment, don't say that. I gave you 2 assignments at that time and I said the app will come later. Please don't do that because I know very well that I gave you the 2 assignments that you were supposed to work. I said use this app to create an impartial equivalent frame for that slab, the same. Don't. I showed you the frame, I gave everything to you. And I said you will do it after the midterm because the app is not ready yet. 2 assignments were given to you. One was to compare the beam bending moment with code and the program. You remember that? No, you have to remember it because I did give you this assignment. You want me to open it? I gave you clearly, I showed you when we were talking about gravity load resisting system, I showed you a slide in which I showed you the ACI formulas and with coefficients, and I said Your assignment is to create an analysis model and get the bending moments and compare them. Are you going to tell me no? You cannot say no, because I remember very well when I gave those assignments to you people. My goodness. This slide. Remember or not? You don't remember? Yes, then why are you saying I didn't give the assignment? The assignment was very clear, and you must do it now. You must compare this bending moment coefficients, create a model, and compare these bending moments from the program and for yourself, and send me the assignment. And don't say next time. I have a recording. I will show you the recording now. I have the recording for each assignment. So if you people have no memory, that's too bad. So assignment number 1, compare these bending moment coefficients from the moments that you get from frame 2D for a beam. Assignment number 2, this is a slide that I showed you last time, comparison of the stiffness of the beam and column on bending moment. And you forgot completely, just before midterm. Equivalent frame. I asked you to generate this. This one. I said take a equivalent frame. I showed you these slides, and I said create a frame of a flat slab strip and create an equivalent frame by using the frame and then putting the stiffness on that based on the actual sizes. We talked about this. I showed you these slides, and I gave you same example. I said follow this model here and use this one to distribute the bending moments. So second assignment is to take one strip from your model. I told you from the project, take one bay and then convert that into an equivalent frame and do the analysis for gravity loads. If you do not know, read about it. And so basically the idea was to take this strip and calculate these bending moments using this approach, because I especially asked my team to develop the program so you can assign different properties. And we talked about calculating equivalent, where is that? This whole thing, strip, equivalent, this strip. We talked about that. Take a strip, put all the things there, and then I also showed you example how that slab can be converted into an equivalent frame like this. So I asked you to just take one floor and create an equivalent frame, including the stiffness of the column and everything. And I said, okay, I'll give you the program after the final exam. But does not mean the assignments is not there. So please do those with 2 assignments. I did not give you the program just for fun. Okay? And I heard somebody went to my office asking them how to share the model. The button is right there on the app. There's a button showing share, and you can't even press that button. to share the model and go to my office and ask them how to share the model? So surprising to me. You know, you're young people, explore things. There's a button on the app which shows directly share, the standard share button that you use in WhatsApp all the time for sharing pictures and on other. Why can't you just share the model the same way? We specially put the same icon to put there. Very strange and disappointing, class. I now put it on record, video, that everybody will see that this is disappointing. So to use this program, use the beam to do the first assignment, and use this partial frame, equivalent frame option to do the second assignment. All right? So now we talk about the behavior, difference of behavior between frame and shear wall. Like I mentioned, frame behavior is due to the bending of the beams and columns individually, and it is, so that means the frame deforms in a bending mode. So everything is curved. This column is curved, the beam is curved, and so on. Shear mode is that no edge is curved. Each edge remains straight. It just becomes horizontally deformed. So this angle called shear angle, it changes, but the edges remain straight. This is the main difference between a shear deformation and a flexural deformation. A flexural deformation, after a displacement, each member in that structure becomes deformed along the entire length, goes through curvature, double curvature, single curvature. And because of that deformation, bending moments are created, shear forces are created, and this displacement is a summation of all the displacements in all the members. However, in a shear mode, the structure simply deforms and becomes deformed body, but edges remain straight. There is no edge rotation, there is no edge deformation. So the body, there's a whole body in between, and it just becomes a parallelogram rather than a square or rectangle. So this is a shear mode, this is a flexural mode. So the frames deform in flexural mode, and shear walls deform in the shear mode, but both of them we call shear raking. Internally it's different, but outside effect is the same, right? So when you put these things together, they behave differently. In some location this is predominant, in some location this is predominant. And this ratio of delta over H is called the drift. And that is the most important item that we look for in tall buildings, drift. And because of the drift, everything comes later. And drift is caused by horizontal forces, shear forces. So shear force causes this drift. This drift causes shear force in column, which cause bending moment and so on. This drift causes the shear change of angle, shear deformation in shear walls, which causes internal stresses, which also then causes tension, compression, and shear, which causes ultimately what? And what does it lead to? What does it lead to? Please don't tell me you cannot answer that question. What does shear and axial stresses lead to? What does it lead to ultimately? What does it lead to? Principal stresses, Mohr circle. We spent so much time last year on that. Axial stresses, shear stresses, you put them together, you get principal stresses. Please tell me, don't tell me that we didn't study about this. We studied, but you don't remember. You cannot relate one thing to the other. What is the purpose of this teaching if you cannot relate one thing to the other? Really strange. So that's the thing. For this one, we are talking about principal stresses caused due to shear and axial force, axial stresses. Here it is bending, shear and bending forces. Bending force is called bending moment, cause bending stresses, and shear stresses. Again, ultimately the same way. The only difference is here there is no material, so everything is concentrated on these members. Here there is material, so all the stresses are distributed. So now you can see this is story mechanism. This is what we call story mechanism. That means if at any story in a tall building or any building you form these hinges, that means we have failure in these all those joints, then the building will collapse, right? Because it will just become a mechanism and fold. And that's what happens in earthquakes. You have seen so many pictures, many buildings in Nepal and other places, they just fold because one story forms a mechanism. The columns top and bottom, they form hinges and they clip and it becomes a pancake. And that's what we don't want to happen. So the purpose is to prevent this from happening by adding elements that can take care of this kind of deformation. Shear walls are one of those elements because they cannot have this kind of mechanism. Normally they have material inside, so they prevent mechanisms from forming. So if the building has a shear wall, it's unlikely that it will become a mechanism. Very difficult for that to happen unless the wall is really badly designed. So if this is the shear wall, this is the any shear panel, and the shear wall can be thought of being made of invisible columns and beams. So if I take this wall and I divide it into invisible columns and beams, right? Let's say this is the shear wall and I say there's a column here. Next to each other, there are columns side by side, right? One column, another column, 1 meter, 1 meter, every 1 meter. Let's say I think that the wall can be divided into columns. And every one floor, I can divide it into beams which are 1 story high, right? So each column can be assumed to be 1 story high like this. Each beam, each column can be assumed. So we can think of the column of the shear wall made up of these fibers. These are called fibers. And these fibers are linked by very deep beams, 1 story high beams. So these beams have very large stiffness, so they don't deform. So the whole, so you can imagine, so now if you go back to my previous slide, this one, just imagine the same frame. Let's say this is a solid wall. Then in that case, the columns will be very big, and these beams will also be very big. So then it will behave almost the same as a real shear wall. So shear wall can be thought of consisting of vertical elements and horizontal elements, but they are so big that they are very stiff. So that you will get the same behavior, similar behavior as a frame of that kind. So, and it will deform like this. As we reduce the column size or beam size, it will start to be closer to frame. And when they become very small, it will become pure frame. So there is a smooth transition between a pure frame and a shear wall. They are the same. They're not different. Only opening starts to become larger and larger and larger. And opening starts to become smaller and smaller and smaller until it becomes zero. So there is a smooth transition between the two. And during that time, the behavior changes from pure shear to pure flexure. And in between, it will be a mixed behavior. Right? So this is a pure shear behavior. This is a pure flexure behavior. And when you put these side by side, they interact with each other, because for a pure wall behavior, it will bend as a cantilever. So it will go like this. So in the beginning, there will be very small deformation close to the base, as you can imagine. And as we go up, the deflection will become large, right? So if you have a cantilever close to the support, there will be no deflection. As you go to the tip, it will be more deflection. But frame is opposite. The maximum deflection in the frame, if you go back here again, is here in the beginning. See? Lot of deflection comes right in the beginning. So frame deform in this way. They deform and then become a little bit straight because the forces above become small. So here all the force, so you can see the top, the frame is nearly straight and most of the deflection is happening in the lower floors. Same here. Most of the deflection happening in the lower floors. So frames start to deform right at the base. Shear wall does not deform at the base, but continues to deform at the top. So which means the two are in the opposite mode of deformation, and that's very interesting. So in the beginning, this frame will try to move away from the wall, but the wall will try to stay here, so the wall will pull the frame towards itself. As we go up, the wall will try to bend, but the frame will try to remain straight. So then the frame will push the wall back. This is called frame shear wall interaction. Because of the deformation pattern between the two types of structures is opposite. Only in the middle, they will be more or less similar. They will not have much forces. So when you put a frame and a wall together, they start to pull and push on each other. This is frame shear wall interaction number 1. There is also frame shear wall interaction number 2, which is the outrigger effect, which I will come to later. So if you just connect one frame to the shear wall just by very thin members, it will still reduce the total deflection because the deflection pattern is opposite. So this is good, right? So this was observed by some people long time ago, and then now if I do that, I have two frames. I have a one frame and a wall, and here I connect it by a small link, medium link, and large link. So then you can see two effects coming together. In the first one, only the interaction effect will be there, the deformation interaction effect, but no spandrel effect, no outrigger effect. This one will be both spandrel as well as interaction effect, because this element will now also try to transfer forces, vertical forces, shear, from here to there, right? So this is very important to realize that when you put a frame and a shear wall together, you get two benefits. Benefit number 1 coming from their different deformation pattern. Benefit 2 coming from the outrigger effect. Because if you go back, actually this figure is not correct. Yeah, this figure is correct. So you can see here that the top of the wall will not be straight. It will become like this as it deforms. But if there is a frame here, that frame, this will try to keep this wall straight. So there will be a vertical shear developing between this and the frame. And that will try to push the wall and also support it by the outrigger effect. So that's what's happening here. So you can see from here that the deformation pattern is different, and this deflection is smaller than those deflections. The shear is, this is the bending moment between those. So you can see large bending moment here and large shear. This is the axial force. You can see now clearly that the bending moment is now converted to axial force. Very large axial force in this column. This is axial force in the column. Very small axial force in this column because there is no outrigger effect. No shear is being transferred between this and this. They are all just bending. But here we can see that some of the bending is being converted into axial force. Here a large amount of axial force is being generated. So a lot of bending is being converted into axial force, which is very good. One of the 4 rules, if you remember them. resists the lateral forces by axial forces. So if you can do that, this system will be more efficient. And you can see the shear force. Here, very small shear force developing in those link beams which are small. When we increase the link beam, the shear force becomes large. When we increase the link beam further, shear force becomes very large. So this shear force is the one which is transferred from this to the frame and stabilizing the whole structure and converting the bending into axial force through shear. Clear or not clear? If somebody is not clear, tell me now, because I'm going to ask many questions about this in a few minutes. So you can see also from the number, axial force, you can see here the axial force in this column is 53, 36, and only 7 kips or kilonewton. And you can also see the axial reaction here. So here 129, 93, and 76. That means the bending moment in the wall is reducing. Tension compression in the local bending moment in the wall is reducing, but that bending moment is now shifting to the next column. So by studying these supports and forces and shear in the frame, you can understand a lot if you want to, but I don't think you people want to understand anything, it seems to me. Because you're not paying attention to these details. So when you look at a model from ETABS or something, please try to understand what's happening. Where are the forces going? What is the mechanism of internal force resistance to the outer forces? And can you improve that mechanism? Can you shift something around? Because it's all a game of resisting the forces, lateral forces, by the most efficient manner, right? Try changing things. These diagrams that I showed you is easy for you to do. In ETABS, in other programs, just change something, see what happens. Understand why it happened. So, combining the shear walls and frames is a very efficient way to solve this lateral loads response problem. Because we get two benefits. One, as I mentioned to you, the deformation pattern is different, so they push and pull at each other, reducing the deflection. Second is that you convert the bending moment into axial forces through the spandrel effect or the outrigger effect. And that is also beneficial because you reduce the bending moments and you also reduce the displacements, right? So that is a good thing. Then comes coupled shear walls. Combining two shear walls in the same way as we combine a frame and a shear wall, you get benefit. I showed you earlier. One shear wall plus one shear wall is equal to 2. If you couple them, you get how much? 4. Okay, in that case 4, it could be more, right? It could be less, up to you. How many outriggers you provide and how much you can do. So you can, I said that all. So basically that's what we are doing. So if there's a wall here, there's a wall here, we can interconnect them by beams or spandrels as we call them, or link beams as we call them, and that by using and controlling those link beams, you can improve the behavior. I often tell everybody, these link beams are your friends in a tall building. Also your enemies, if you don't know how to use them. So if you know how to use link beams, they can be your best friend. Place them in the right location, size them in the right manner, assign them in the right, configuration, you can benefit a lot. If you don't understand, they will create problem for you. The first problem normally comes that you get too much shear and bending moment in these beams that you cannot design for. But if you know how to size them properly, how to detail them properly, you can then get benefit, because these link beams absorb most energy. They have the most ductility. They give you the most stability. So you can use them in a variety of good manners. So the thickness, the ratio of the height of the link beam to the height of the floor is an important parameter. how much deep that link beam can be. Normally, architects will not let you have large beams here because there's a door for the elevator below that. So sometimes, like I mentioned, you compromise, you bargain. You tell them, okay, I can give you lot of space on all the floors, but give me 1 or 2 floors where I can increase the thickness, and you can put the door somewhere else. Or just give me one location where I can put a big beam and I can give you all the other free. Like that. So you can bargain with the architects on these things. That's what you, so this is the big beam, some small beam, some different sizes beam. You can use that to your advantage if you know how to do that. 1 or 2 big beams may be all you need, and you can give them all the other small beams. So that's the way. So when you connect them, this becomes your connected model. So we studied coupled walls in another example, which you can do by yourself also if you want to do that. Just very quickly create this model. So here I put a very small beam, I keep increasing the size of the beam, and from that you can see how it looks like in configuration. And here the deflection, you can see from here, deflection is that much. Same walls, deflection is reduced to that much, and only that much. So this deflection is much, much smaller than that deflection over there, right? So effect of the coupling beam is the highest in the lateral load response. But sometimes the forces that you get in these beams are too large and you cannot design the reinforcement. So sometimes we have to let it yield. So we do a capacity-based design. That means we fix the capacity of the link beam and we fix the bending reinforcement, and in such a way that the bending failure will occur before shear failure. I gave you the example of the previous class. What did they do? What did your previous class do to prove this point? I explained this to you. Unbreakable beam. They created an unbreakable beam in which they provided the reinforcement, flexural reinforcement in such a way that bending failure will occur before shear failure. So the beam could not be broken. It deflected a lot, but it never broke, because it can break only in shear. Bending can only cause deflections, not failure. You know that, right? You can bend something like this without breaking. It will only break when it breaks in shear. Bending does not cause failure. Shear does. May I break this? See, this is, I'm bending it. I can bend it that much. Can you imagine this deflection? This deflection is more than the length of the beam. I have no problem. So bending is not an issue. You can let something bend. So you can say this plastic beam is unbreakable because I was able to bend it so much, it didn't break. Of course, if I do quick, but that's going to be local shear to failure here. I'm going to break it. Right? So we try to prevent brittle failure by allowing these to yield first before breaking. Then you will have a nice link beam which never breaks, at the same time carries loads as much as you want. And that is the way we design the link beams, to be ductile in bending in such a way that the bending capacity is always less than the shear capacity. So it starts to fail and it cannot attract more, because if the bending capacity is small, it will start to bend like that. So the shear will reduce and it will not break. Before it will be like this. After it starts to be yielding, it will become like that or like that, which is fine to us, right? As long as it doesn't break. So link beam design, you can see from here, large shear as we increase the sizes. Axial stress is changing in walls. Here becoming almost tension compression. Here local bending. So from that, this is pure bending of the tension compression. Here tension compression. So you have moved the local bending of each wall to axial stresses in the two legs. And that is much more efficient than bending. Yes? No? And that is the shear in those links. That is the bending moment in those links. So normally we design the bending moment to be limited in such a way that this shear does not exceed the shear capacity. Right? So one of your assignment of your project will be to design the link beam. So when you go to the design of the link beam, remember that you design it properly. And you can see the axial forces developing in each case here. Look at this one. Please watch this carefully. Here, each wall has a tension, compression components locally. In this case, the entire leg is in tension and entire leg is in compression. So that means now you have this very efficient system, not local bending anymore. Local bending is completely gone at the base of the wall. Any questions so far? So now you understand why certain systems work better than the other. There is a whole logic behind that. And the logic is simple. Convert bending to axial forces. Use the effect of the outriggers, right? Connect things in such a way that 1 + 1 is more than 2. So we have already talked about belts and all. This is the outrigger, so this is the wall, this is the outrigger, and the location of the outrigger, size of the outrigger, that is something that you can spend a lot of time trying to optimize. But sometimes you don't get this because architects want opening in there. So sometimes the outriggers are with holes in there. And again, we had one of our senior guys do research on outriggers with holes. What happens to those, right? So this is the effect of the outrigger. Top, middle, no outrigger. For a short building, you cannot see much, but still, you can see here. Displacement pattern, you can see how the axial forces. So you can see above the outrigger, there is no axial force in column. Below the outrigger, there's a lot of axial force in column. So the outrigger transfer the bending by axial forces to the column. These are called mega columns. Here, outrigger is here, so the entire column has axial forces. So stresses in the wall and column because of the outrigger. Moments in the columns and shear in the column. So you can see all of. So you can study all these things easily. And sometimes, like I said, outriggers with openings, ductile wear and deal frames. Sometimes you cannot have an outrigger. So you put these. Do you know this term? Wear and deal frame. How many people know? Raise hands. Do you people know? Oh, we know one know. Okay, at least one person knows. Wear and deal truss. Wear and deal frame is a frame or a truss with no diagonals. So it carries the action by pure bending. It's like a frame with high rigidity. How many people have gone to Asok intersection in Bangkok? BTS, Asok BTS. So you never leave AIT, right? Terminal 21. Yeah, that walkway. That walkway bridge is a wear and deal girder. So if you want to really see a good example, you should go this weekend to that place and walk on that bridge on the Sukhumvit. Take some pictures and explain to me how that works. I could give you assignment, but then you will ask me to arrange a trip and give you the, arrange a van for you to go there. But that is a very good example of wear and deal truss they use on that walkway bridge. One of the few bridges where you can see that very clearly. So they designed it as a frame, but it's a truss. So it's just with like this. So sometimes we can design outriggers with openings using the wear and deal ductile moment frame concept, right? And here, capped wall, sometimes you put the outrigger at the top, sometimes we call it cap. So if they don't allow you to put here, you put it at the top, which is also fine. I showed you earlier also. This is the effect of the outrigger on the deflection shape, location of the bending moment change. So you can study all those things by changing the location of the outrigger. Many times we have done this study. What is the best location of outriggers? How many outriggers will be good for a 70-story building? 1, 2, 3, which floor? 20th floor, 40th floor? So it's not by accident that you find. You need to understand how the system works. So we have found many times how many outriggers are more effective. Sometimes we combine outriggers and BRB. Sometimes combine outriggers with belts and flag walls and BRB. So you can, like I said last time I told you, you are like a chef. You have all these ingredients and you have to create a nice dish, right? So some of that, some of salt, some of that, combine some, different cuisine together. Something from French cuisine, Thai cuisine, they call fusion these days. So create a fusion model of your structure, borrowing ideas from here and there, putting them together, trying them together, and see what works. Don't be limited by traditional classification of the system. That's why I give you a real project to play with. Play with it, right? See how different things work. Try changing some things. Look at the response. Look at the initial period. Look at the forces. Look at the bending moments. You can learn a lot. So this is the effect of the outrigger. So you can see at the top, at the middle, the deformed deflection shape becomes like this. Bending moment becomes like this. Another location, so like this. So people have worked very small. People have worked on these things and then found that, okay, the best location is here for a single outrigger. After plotting all these things, they see the most effective location will be here, around in a 46-story building, 26th floor, around. You can plot this curve for anything. So that will be the best. And you can, of course, study other options. So there is a way to do this. So that's the outrigger that is considered to be a good location for a building of medium height. When you have higher, then you maybe need 2 or 3. Typically, an outrigger is effective to 20, 25 stories. After that, it starts to be, again, a problem. So this is the single belt truss. So they compared many things and plotted. So this is the optimum location for that. This is also part of a thesis, not from from AIT, some other research, just only studying the outrigger location. So recommendation for optimum location, this is the recommendation. If only one, it should be this one, 2 like this one, 3 like this one, 4 like this one. So this is the final conclusion from their study, right? But it is only for their study. It may not work for you, depending upon how many bays there are and what is the configuration, size of the shear wall. Many things are important. You cannot generalize it completely. This is from their study, for their model. Your model may be different, so don't believe it completely. Haunch girders sometimes we can use to increase the stiffness and increase the outrigger effect. So this is what I was telling you about. If you take a solid wall and I put some opening there, so this is a wall with opening, right? I'm not so sure this is a wall with opening or it's a large column and large beam. You can say anything about that. That one is large column and beams. This one is definitely a frame, right? But it's the same. I just started with one solid wall and I started to put some openings in there. So in first case, you can call it wall with openings. Second case, you can call it wall with large openings or frame with large columns. Any one of the definition will be okay. Next one, and this is pure frame. So from pure wall to pure frame, it's just a transition. You don't need to treat them completely differently. They're just a transition from one behavior to the other, depending upon the relative sizes of the frames and shear wall openings and the columns and the beams. So you can optimize this in anywhere in between, depending upon what is the condition. So you can see displacement 15, 0.7, 0.2, 0.13, so pure frame very small, displacement is very large, pure wall very small, in between it varies depending upon how do you have the outrigger effect, right? So you can say that this displacement is, this stiffness of this frame is about 45 or 50 times smaller than that one. And this one about twice, this one about 5 times, something like that, right? So by changing the relative stiffness of the columns, beams, and openings, you can attain different stiffnesses or stiffness behavior as you want. But of course, many times architects and other requirements will govern that. This is about shear lag. Same thing. How much shear can the transverse connection carry? That's called shear lag. If the transverse connections are very weak, shear lag will be large. Perfect situation is when you have linear strain distribution, like a beam or a column, and as the shear lag comes, the linear strain distribution becomes non-linear, like that. So you should read about this one. Please read about this effect of shear lag. I will ask in the exam a question about these few slides. So please read them carefully. Read all these slides. I'm not going to discuss. Okay, last few minutes. Tubular system. I don't want to discuss a lot about tubular systems because last time we talked about it a little bit. Basically, tubular system is this same thing that I mentioned to you. It's a wall with openings. So it's a tube with openings. So if you consider a building outside to be as if it is a wall, and then you put some openings for the windows, then it's become a tubular system. And tube can be of any shape, any cross section. This whole building becomes a cross section of a cantilever with a tubular cross section, just like this one. So if you can go back, this one is like a tube. So this is the building. You consider it as one tube, same way as we consider this one. And this is a tube with closely spaced columns with small openings, and as we go along, keep increasing the size of the opening, it becomes a frame. So we are talking about a tubular system where the openings are small compared to so very small opening, small spans of the beams, very closely spaced columns, so they have small shear lag. Sometimes we put diagonals. So this is a tube, and when you put the diagonal, you increase the stiffness and reduce the shear lag, just like a truss. Sometimes we can bundle them. Tubes can be put together and they act together. Many buildings are now based on this concept. Bundle tube, bundled brace tubes. Very tall building, 300, 400 meters, they normally use this concept. This is another example of bundled tube, 3 tubes bundled together and different heights. So these different heights are very helpful in wind design, because when you study wind engineering, you will notice that the building has this behavior of the crosswind oscillation, and that can be greatly reduced by breaking the building heights at different levels or changing the building shape. So this is quite helpful in that. And then there are miscellaneous systems where you can combine. This is, I showed you many already: wall with the frame, diagonal braces, super trusses, and so on. All right. So that's the end of lecture 8 and 8A. we have no time, but I want to still ask you, what did you learn or did not learn today? Very quickly, 30 seconds each. Important observation today.
The structural performance can be improved by converting bending moment to shear, and also the lateral deflection, it can be far reduced by outrigger effect.
You have taken the comments from everybody else. I mean, other will. Okay, next one.
I learned about the effect of frame and shear wall interaction, which different deformation pattern, and also the effect of outrigger.
Okay, next one. Okay,
Effect of coupling beam in shear wall is very important to reduce deflection from lateral load.
next one.
We learned about the importance of outrigger effect and how it can help to optimize. No, that's not the word. I think like it can help to change the stiffness and get greater efficiency.
Okay. So same one. That's why I say what you said is everybody is going to say that. Okay.
This is about concept of strong shear connection and shear wall and outrigger.
I learned that how frames and the shear walls can be used in the same building and they help to reduce the deflection at the same time.
Deflections and also bending moments.
And then this will really that it helps with the frame also helps with the shear wall. And then I also learned that the coupling beam is important to help the framing system.
Yeah.
And then we really need to learn more about coupling beam because if we don't, yes, we will have really large shear and bending.
Right. Okay. The lecture had 50 slides, so please look at other slides also. Mm-hmm. Good. Okay.
This for the frame deformation pattern and shear wall deformation pattern. By knowing that now, we can retrieve the deformation pattern by using outrigger award and also can retrieve the bending moments and can transplant AZ walls to the collar.
Okay. Good. Yes.
Main concept is that the bending moment converted into aperture here and the pattern of design for tolerance or gripping is almost opposite because gravity and weight load are the two different factors involved.
Good.
When we couple two shear walls together, we need to think that when we combine 1 plus 1, it should be the greater than the stiffness.
Very important. Yes.
I learned about the story mechanism, like when the hinges are formed, the buildings collapse,
Can collapse.
crumble.
Yes. Must avoid that. Yes.
Another is the couple, if you connect the two couple walls to sufficient beam, so we have like units, like one will take tension, another will take concrete.
Excellent. Next one.
About that, in order to achieve the ductility design, we need to design a structure which the fracture yielding first before structure need the capacity shear.
Excellent. Very good point. Yes. Yes, that's true. Okay, good. All right, thank you. Do not forget to do the assignment on Frame 2D. If you cannot use it, then we have a problem. And send me your models. If not today, Saturday, Sunday also can send.